The whole idea that we talked about last time was we had this setup where we had a ruler. Whoa! What's a real world problem again? Measure with data. Okay, so we have this hook or this kind of post here. There's one end of a spring that is immovable. I literally can't move this. If I pulled it, I would ruin the spring. There's one end of the spring that is movable. And then what I do is I put a bunch of different masses, and then I literally measure. Like, one thing I have to measure is what the masses are. That's not given. And you saw that there was a scale associated with that. And then associated with each mass, I measure a particular position along this ruler. Right? And then I just keep doing that until I get a full data set. And what was the claim that I stored that data in? Column vectors. Yeah, so Excel I have a lot to say about. I'm upset with Bill Gates because he labels columns first and then rows second, which just bothers the heck out of me. But we said let M, we're going to let this be M1, M2, M3, all the way down to M, I don't know, maybe we call it sub N. Could you guess what N is? N equals number of rows. What's another way to say number of rows? It's the number of measurements that we collected. It's the number of times that we physically captured the weight in a scale and then physically hung those on that scale, right? Then we're going to have what we call an X vector. And this is going to be X1, X2, X3, all the way down to Xn. Could you guess what those are? The raw position of the movable end of the spring. Okay, so here we go. Do you see my mass matrix? Or my mass vector? All matrices are vectors. All vectors are matrices, not all matrices are vectors, right? Do you see my mass vector? There it is. So I think I might have been using a different weight set. What are you noticing? How long do you think this took me? Long time. That's called given. Right? You know what a mathematician would do? They'd round up. Mathematician would say, oh, this is discretized. They would say 0.01, 0.02, 0.03. Right? And then they would literally just say, oh, go from 0 all the way up to the end, right? Okay. And then what about the, so here, do you see position below ground? So in this case, which way is the positive direction of my ruler? Is it above the mass or below the mass? It's below the mass. Why is it below the mass? The larger the mass, what happens to the position? The more it gets pulled. Okay. So now all of a sudden we graph this whole thing, and let's see how many data points we have. It starts at 5, and it goes down to, let's see how many this guy took. 45, that's called an overdetermined system. Okay, so that's 40 different data points. Okay, we didn't do any math on this yet, right? How do I zoom out? So let's see, review. What's that? Control minus, that's the easy way to do it. What do you notice about that relationship? What does it look like? Linear. Well, if you were only 500 years older, it might be called the Katya law rather than Hooke's law, right? Because that's exactly what Hooke figured out. If I map masses versus displacements, it looks linear. Okay, and we're going to use in just a bit when we get into lesson 4, we're going to use matrix or vector arithmetic to actually formalize this and to construct a least squares problem from Hooke's law. What else do you notice about that data? Is it exactly clean? No. If I actually drew a line from that, what would you know? Would all of those points lie exactly on the line? No. Why not?
Imperfect measurement.
Imperfect measurement. In other words, the B that results is in my codomain, but not my range. It's called a least squares problem. That is a least squares problem. You're looking at a least squares problem constructed from real data. And we will, by lesson 22, we will actually construct this thing and solve this thing so that when you're given a spring and you see a K, you will indeed see somebody that solved a least squares problem. All right, so that's your first example of a real world problem live in class in front of you.